All right, it's 1 o'clock Central Time. We're going to go ahead and get started. Hello, everyone. My name is Matt Delacluse, General Manager of RaecoRents. I'd like to welcome everybody attending our webinar on sampling pump calibration and reporting. Our presenter today is Aaron Apostolico. In this 45-minute webinar, he will cover the following: the importance of reliable sampling pump calibration, using calibration data to anticipate pump performance issues, supporting documents for calibration, new advancements in pump calibration technology, and at the end, we'll do an Ask the Expert, your questions answered. Aaron serves as product line manager for occupational health and industrial hygiene instruments at Sensidyne. He has proven experience in evaluating safety hazards, risk analysis, safety program audits, compliance review, and development and implementation of safety programs. He holds a Bachelor's of Science degree in Environmental Science from Rutgers University. He attended the University of South Florida's College of Public Health for graduate studies in occupational health and safety. He holds professional designations as Certified Industrial Hygienist, Certified Safety Professional, and as a Certified Indoor Environmental Consultant. Welcome, Aaron.
Thank you, Matt. And welcome everyone who is joining us today. I appreciate you guys coming out, and I appreciate RAECO hosting this event for us. I'm going to jump into our presentation here. As Matt mentioned, I'm the product line manager for Sensidyne. We do manufacture a wide variety of health and safety equipment, but for today's purposes, I'm going to be talking in a lot of general terms about best practices for calibration and reporting those results and keeping the appropriate records. So my presentation overview, I want everyone to understand what is reliable calibration, what supporting documentation is required, and advancements in calibration technology. As we discuss the importance of reliable calibration and air sampling, we'll go over what type of documents and records you might have to maintain, and of course, always consider that any air sampling you do may have to be defensible in the court of law. Additionally, we'll cover some specific advancements in air sampling calibration and different methodologies that are currently being used to track pump stability and create permanent reports in defense of your sample integrity. So when we talk about calibration, there are different types of calibration that are out there, but calibration itself is the process of adjusting a device to meet the manufacturer's specifications that are within the industry standards and requirements. Calibration can also be defined as the issuing of a report or certificate of calibration that declares a product's conformance with a specification or standard. The second definition I mentioned is more properly referred to as certification as opposed to calibration. And as we proceed with this presentation, we'll talk a little bit more about those differences. So when we think of reliable calibration, there are four aspects in mind that should be considered. The first is third-party traceability. The second is the accuracy of our calibration. The third is the precision of the calibration. And the fourth should be the stability of the calibration in line with the airflow source that is being calibrated. So third-party traceability is typically done by a National Meteorological Institute. In the case of the United States, we use NIST, which is the National Institute of Standards and Technology. They are pretty much the forebearers of what a standard unit of measurement is for consistency purposes all across the nation. And of course, NIST works with other units around the world to make sure when we say a cubic centimeter is a cubic centimeter, it's measured as a cubic centimeter the same everywhere. They are also the holders of the master volumetric devices used for primary calibrators. So third-party traceability can also include organizations like ISO and IEC. So 17025 is a specific ISO standard used by testing and calibration laboratories, and labs must hold accreditation in order to be deemed technically competent. As I mentioned, there is a National Meteorological Institute at the top of the measuring equipment hierarchy. They represent the basis for determining the values of all the subordinate standards of measurement. So in this case, you have your pump that you're trying to calibrate, or other air source. And then you use a calibrator to calibrate it. That calibrator should be certified by an accredited calibration laboratory, and that the accredited calibration laboratory should have certification or traceability back up to the NMI. As I mentioned, NIST is a part of the U.S. Department of Commerce. They oversee the development of measurement standards for any international system of units. So this includes everything from meters, kilograms, seconds, amps, Kelvin. They pretty much are the top of the food chain when it comes to that certifying traceability. Now, countries around the world will utilize their own regional meteorological institutes and laboratories to set the basis for their own standards. Because of this hierarchy, though, the traceability calibration exhibits an unbroken chain. Basically, this means that if you sample under the unit of measurement in Brazil, it should mean the same unit of measurement in England and Australia and the United States. All the measurements obtained with traceable measurement equipment are traceable to this standard and will therefore be comparable to each other on a worldwide basis. The provider of NIST traceable measurements may be NIST itself or another organization. Now, there's thousands of companies that tie their measurement standards to NIST. They may then follow these standards in providing measurement services to their customers, in meeting regulatory regulations, and in improving quality assurance. So an accrediting body here in the United States is A2LA. A2LA then certifies calibration laboratories, such as Sensidyne's calibration lab, for compliance with those standards. Now, the International Organization of Standards, ISO 9001 and ISO 17025, are used around the world as the preferred criteria to form the basis for guiding calibration and certification processes. Scientists and IHs use these standards to ensure the occupational health sampling is both reliable and the results can be used with confidence. The ISO 17025 standard addresses the requirements for specific competence of testing and calibration laboratories, and in most major countries, the ISO 17025 standard is required for laboratory certification in order to be deemed technically competent. The essential characteristic of a calibration certificate is traceability of measurement results, and thus its international comparability. So as I mentioned before, there are several types of certificates that are on the market used to document the accuracy of the measurement and the equipment. They're not all held equal. Note that a NIST calibration certificate is not necessarily an ISO 17025 calibration certificate, and that the ISO 17025 certified calibration laboratory are typically held to a higher regard and deemed more reliable. So these certificates for the ISO 17025 contain a measurement of uncertainty, which the NIST certificates typically do not. This is a determination of the measurement process, and independent assessors must also examine the suitability of the process and the measurement in order to assure that traceability. So this is where calibration laboratories are audited by another third-party group to ensure that they have a sound process and that the traceability of the units that go out the door that they calibrate can actually conform with the national standard, and in this case, to NIST. According to the ILAC, only inspection laboratories accredited to the ISO 17025 are permitted to carry out traceable calibrations and thus guarantee complete international comparability of the calibration results. Therefore, equipment that was simply calibrated with a traceable measuring device is not itself traceable, since the measurement process was not performed in accordance with an accredited procedure. So the user or field calibrations are more accurately defined as a calibration verification rather than an actual calibration. So let me break this down. There's a lot of technical jargon that I just went over, but I just wanted to distinguish when a field calibration is performed with the calibrator that is used in the field. That is a calibration verification to make sure that the unit that you're calibrating, the air sampling pump, all right, conforms within a certain degree of the calibrator. However, that calibrator itself, in order to be certified calibrated, needs to have that traceability back to that NIST standard. Excuse me. Next, we're going to talk about accuracy. Now, air sampling for environmental and occupational health purposes cannot be depended on unless the equipment utilized is appropriately calibrated. Through calibration adjustments made to a piece of equipment to ensure that it performs as expected and can be relied upon to deliver predictable, accurate results that will meet the required quality standards. As a CIH for many years, I've had to make some critical decisions on whether to protect the health of the worker or to put additional engineering controls in place, and I rely heavily upon my air sampling results to make this determination. Well, my air sampling results are only as good as the quality of air sampling calibration that is being performed on the pump being utilized, as well as the laboratory services being utilized in the preparation of those results. Now, the accuracy of the calibration device or calibrator should be at least 2 times greater than the equipment being calibrated. Although 4 times is the preferred minimum, 2 times is an acceptable limit. The equipment usually has a calibration range over which the end user will check the specifications. It's important to make sure that you match up and you align the right size calibrator for the right size airflow source. In other words, if I'm sampling or trying to prepare a low flow sampling pump, I'd want to make sure that I was using a calibrator that had a low flow specified range that I could accurately measure the airflow and calibrate my airflow source. Now I want to denote there's a difference between accuracy and precision. Now these are 2 ways of measuring targeting. Although accuracy is intuitively understood and desirable, precision is often confused with accuracy, where the measurements are not representing the true value. If successive results agree, a false sense of confidence may be formed that is not merited. So when a group of results are precise, they have minimal deviation. When they are accurate, they are close to the desired target. So in the illustration below, all right, the illustration to the far left is both accurate and precise. You can see that there's a very tight shot group in the dead center of the target. This is what we want. However, you can be precise but not accurate, which is the second bullseye, which shows a tight group but away from really that targeted, or in this case, the desired flow rate. The third one that you see from the left is accurate but not precise. If you averaged out those 4 dots, you would get an average that was very accurate, dead center of that bullseye. But in this case, it's not very precise. And I'll explain how this can be illustrated with some of the sampling. And then, of course, the last illustration there is showing neither accuracy or precision as the shot group is kind of spread out as well away from your targeted bullseye intended calibration flow rate. So when considering the accuracy of your calibrator, several basic questions should be considered. Who calibrated the calibrator? And ask yourself, did a competent, trained individual calibrate my calibrator? Do I have a signed and dated calibration certificate? What was it calibrated against? Do I have a calibration certificate that actually references a NIST traceable master device? And that's something that you should look at on your calibrator's certification. Can the laboratory provide the traceability documentation? Usually that's not included with your calibrator. However, if you actually call the calibration laboratory, they should be able to provide that traceability documentation for you. And then have you ever challenged the calibration lab? Make sure that they actually do have that documentation, that it's up to date, and they can actually show traceability. Now, when considering the accuracy of your calibrator, several other basic questions should also be considered. When was the calibrator last calibrated? Is the date of the last calibration printed on the device or on the certificate that you have? It's important to note that most calibrators will not hold a calibration indefinitely. As they get used and sometimes abused, the calibration may become less accurate. So if you go and you get a new calibration or annual calibration performed, you may want to get an as found performed so you can see how far out of calibration your unit was when you sent it in for recalibration. Now, most manufacturers recommend a minimum of annual calibration. However, on a company basis, you may want to perform it more often depending on how you're going to rely on those results. Now, most regulatory agencies require an annual calibration for their calibrators. So I know, for example, OSHA requires an annual calibration for all the calibrators they use while performing those field calibrations for regulatory purposes. Also, when considering the accuracy of your calibrator, you want to know where it was last calibrated. Was it performed at a competent laboratory? Did that laboratory have a ISO 17025 calibration? Also, has anything changed since the calibration was last used? One way you can see if there's excessive abuse on the equipment is to perform a leak check if such an option exists on your particular calibrator. Now, precision as opposed to accuracy. When you consider precision of your sampling calibration results, you must also take into account any factors that introduce bias, and I'll explain how that bias comes into play. It may come in from either the equipment being calibrated, the sampling train itself, the calibrator, or even the environment that you are calibrating in. So some questions you may want to consider. Can a calibrator be accurate but not precise? Some things to consider in that question would be, all right, is there constant flow? Is volumetric or STP, which is standard temperature and pressure, being utilized or referenced? And can pulsation impact the flow rates? And I'll talk a little bit more about that as we proceed. So it's important to understand how constant flow works. Most air sampling pumps these days operate in a constant flow mode. The pump will maintain the same flow rate regardless of the back pressure that accumulates and must fault, i.e. stop running, when the flow rate goes outside the required accuracy specification. So usually that specification is 5%. So if I set my flow rate to, let's just say, 1 liter per minute, and I want it to be within 5% of that reading at all times, a constant flow pump will actually fault out if it goes outside of that plus or minus 5%. Now, this process works a lot like cruise control on a car. So the pump senses when the flow rate is trying to drop, similar to a car driving up a slope, and then speeds the pump motor up to maintain that speed. So as I mentioned, industry standard requires that the actual flow rate be within plus or minus 5% of that set flow rate. Now, when thinking about precision, all right, if your pump is yawing a bit, so you hear your pump, starting to rev and really all right, the motor is probably trying to compensate for an observed change in the back pressure. So in some cases, this can be pulsation caused by the pump itself, caused by tubing or the media holder that it's in. And in other cases, it can be attributed to the calibrator being used to calibrate the pump. Now, these are biases that can affect the average flow rate based on the pump's attempt to maintain constant flow. Additionally, environmental factors may also impact the precision and accuracy of your calibration. Relationships between pressure, temperature, density, and volume must be considered and understood when performing volumetric calculations. It should also be noted that gas measurements are related by the material's density, which depends greatly upon pressure, temperature, and to a lesser extent, the composition of the material. Now, the relationship of pressure and temperature and density and volume as it relates to calibration. Gases are inherently compressible and will change volume when placed under pressure, if they're heated or if they're cooled. A volume of gas under one set of pressure and temperature conditions is not equivalent to the same gas under different conditions. Now, this relationship can be illustrated by using the combined gas law, which is derived from the ideal gas laws, also known as Charles and Boyle's laws of classic chemistry. And I'll show you how this works. The ideal gas laws are utilized to normalize gas volumes and/or volumetric gas flow rates, volume per unit of time. To set a particular temperature and pressure condition, because the volume of gas, air in most cases, is a function of the temperature and pressure conditions at which the gas exists. So in this particular case, you see Charles' law, which is V1 over T1 is going to equal to V2 over T2. Therefore, there is a relationship between volume and temperature. The volume of an ideal gas, when pressure and the molar mass are held constant, is directly proportional to the absolute temperature of the gas. As temperature increases, the volume of gas increases. All right, and you can see that in the picture where the gas is being heated to the right of the equation. Now, Boyle's law says that the pressure over volume, P1 over V1, is equal to P2 over V2. All right, this shows an inverse relationship. Therefore, the pressure and volume of an ideal gas are inversely proportional. While one increases, the other decreases, when the temperature and the molar mass of the gas are held constant. So now when you combine these two laws, you get P1 V1 over T1 will therefore equal P2 V2 over T2, and then you can solve for any of the variables that you have in question. So your pressure is going to be your ambient pressure. Your volume is your air, typically in liters or cubic meters. And your temperature, remember, is measured in Kelvin. And Kelvin is equal to 273 degrees, or 273 plus your degrees Celsius. Assuming the makeup of air is constant, changing the temperature or pressure will change the volume. However, in the case of volumetric devices with a fixed volume or space, such as a calibrator, what changes is the speed at which the gas moves through that fixed volume. Therefore, it is important to know if your calibrator calculates impacts of temperature and pressure on airflow. Some of the older calibrators on the market do not. However, several of the newer calibrators will actually have formulas to compensate for temperature and pressure as it relates to the speed at which the air moves through the calibrator and is measured. So another aspect to consider is correcting the volume based on a reference standard temperature and pressure or a normalized temperature and pressure. Now, STP typically refers to a nominal condition in the atmosphere at sea level. The value is important to physicists, chemists, engineers, as well as to pilots. It should be noted that different agencies around the world will set up or determine what their own STP values are. Here in the U.S., we typically reference the International Union of Pure and Applied Chemistry, or the IUPAC, as well as the NIST standards. They define STP with a temperature of 273.15 Kelvin, which is typically at 0 degrees Celsius, and as an absolute pressure of 105 pascals, which you can see is about 1 bar or 750 millimeters of mercury. Now, in order to correct the volume to a standard temperature or pressure, the following equation is utilized. In this particular equation, you'll see that your V sub S is your air volume in liters at the referenced STP. So this is what you want to calculate. In order to do that, you'll need to know your air volume in liters as measured, which is calculated from your flow rate and the time sampled. You'll need to know what your ambient pressure is. You'll need to know what your temperature is. Again, remember, in Kelvin at the referenced STP. Your temperature in the sampled air in Kelvin, which is what you're measuring in the ambient, and what your pressure is, again, at the referenced standard temperature pressure, or NTP. Again, you should make sure that you don't confuse this STP with your NTP values. NTP is usually a higher value. The US EPA, for example, lists a temperature of 293 Kelvin, which would be 20 degrees Celsius, and an absolute pressure of 101.325 kPa, which is 760 millimeters of mercury. The NTP values are commonly substituted as the reference STP, which is acceptable as long as these values are noted with the corrected volume. So whenever you're using a corrected temperature and pressure, make sure you actually state what your NTP reference values are. Next, we're going to talk about stability. During air sampling, end users strive to have a consistent airflow across the entire sample period, with a max deviation of 5%. The closer the deviation is to 0, the more accurate the calculated volume is over that period, noting that the volume is a function of the flow rate and time. So why are stable readings important? Obviously, as I just mentioned, we want to make sure that our pre-calibration and post-calibrations are within that plus or minus 5%, and also to make sure that there's not back pressure artifacts, which is a bias created by the calibrator itself. So this is a case where stability comes into play. With every cycle of the pump, air is drawn in and then exhausted. All right, this is how the pneumatics of most pumps work. The resulting airflow will not be completely smooth, all right, and it'll include an alternating or pulsating component due to the pump's actions. The pulsation performance is expressed as the ratio of the pulsating component amplitude to the mean flow rate. Now, this is especially important when you're actually sampling using a cyclone for respirable dust or respirable silica. These sampling heads rely on a steady flow to maintain a specific size cut. It is important for pulsation to be as small as possible. Deviation from the specified airflow for a cyclone will result in the sampler not accurately reflecting the respirable size fraction. So in other words, if your flow rate deviates from that sampler's specified cut rate for 4 microns, which is the cut rate for respirable fraction, then it can actually either over-collect or under-collect the concentration at that particular flow rate. Now, with some piston-style calibrators, the piston itself can create an artifact back pressure pulse, which the constant flow pump will respond and thereby create the yawing effect. This in turn creates an unstable flow. So let me talk about this artifact. If you can imagine you have a piston puck that moves within a cylinder. If that puck were to be raised up and dropped, all right, there's a little pulse or pressure wave that gets pushed back to the pump being calibrated. If your pump is in constant flow mode, it will respond to what it perceives as a change in pressure and then speed up or slow down the motor speed. And that will create that yawing effect. Now, if your calibrator is trying to calibrate a pump that isn't steady, it's not going to actually see a steady value. And if you record that value or you change the pump's calibration to a unstable value, it actually won't be displaying what that pump is actually bringing in. So as I mentioned, in the case of some mechanical piston styles, the piston moves from a bottom position. It gets drawn upward. It'll pass a start sensor and a stop sensor. When it falls to the bottom of the cylinder in a free fall, this free fall will create a pulse wave that can affect that pump. The end result is that the flow rate is variable under these conditions, and it will bias the calibrator, which will not be present during the sampling. So in other words, when you disconnect the pump, it's actually going to be running at a smoother rate than it would be when it was influenced or biased by the calibrator piston itself. Next, we're going to talk about calibration reliability and how to preserve your records. So why is record keeping important? How do I maintain sample integrity? What do I need for my report preparation? And then how do I defend my air sampling and my calibration results in the court of law? Being a CIH who has actually performed thousands of air sampling events, fortunately I've only been called, or unfortunately I've only been called for deposition a handful of times. But one of the first things I'm asked by a deposing attorney is, was your air sampling pump calibrated? And then when was the last time that calibrator was calibrated and where was it calibrated? So making sure that I have that type of traceability was definitely critical in defending my air sampling results. So what supporting documentation is needed in general for air sampling? Consider the chain of custody is viewed as a legal document. Any field notes that are taken, and on your field notes, you'll typically want to denote your pump model, your pump ID, your sample ID, your worker or area ID, the start and stop times, your flow rate, your volume, and any relative activities. And then last, but often overlooked, is a calibration log. That calibration log is considered legal documentation and should be maintained. Now, documentation and record keeping are fundamental aspects of air sampling. In order to maintain integrity before, during, and after a sampling event, the operator or facilitator must record relevant data that corresponds with that particular event. There are several key documents that should be maintained as part of every sampling event. As I mentioned, these are the calibration log, any field notes taken, and the chain of custody. These three documents are interrelated and have overlapping information that should be consistent across all three documents. The calibration log has specific details that should be captured as it relates to each pump and sample used during calibration. So these details that should be specifically recorded on a calibration log include the date and time of calibration, the pump model, the pump serial number being calibrated, the username, the sample ID, the calibrator ID, the date of last calibration, the ambient temperature and pressure at which you're calibrating at, the flow average, which is your volumetric average, if need be, the calculated STP flow average, the number of samples in your averaged sample set, the standard deviation between those samples, which again shows that stability, and then the flow rate readings themselves. So this is an example of a calibration log that actually identifies all of those values that I just mentioned. You can clearly see that each individual information should have a line item that is completed, and this helps create that calibration integrity that is required for legal documentation. So additionally, supporting documentation will include the calibration certificate. Calibration documentation varies from one service provider or manufacturer to another. Maintaining a copy of the calibration certificate is essential for identifying measurements of uncertainty, guard-banded acceptance limits, accreditation body symbols, and other provided specific details. As I mentioned, field notes are a critical part. Field notes should capture precise details about the sampling event. These details should align with those in the calibration log and incorporate those activities specific to the pump and media that was used in the calibration. So these details generally include the pump model, pump ID, sample ID, worker, area ID, the sampling method, the media, your start and stop times, your flow rate from your calibration log, the total volume collected, and the relevant activities that were performed. Now, once the post-calibration process is completed and documented, the information will be transferred to the chain of custody. While many chain of custodies vary in format, common details are required. These details generally include customer information, the turnaround time requested, the sample ID, the date sampled, the collection media, the sample volume units, the analysis type, the analysis method, and then the relinquished and received by names, date, and signatures. As you can see from these 3 slides that I just went over, there's quite a few pieces of data that actually are consistent across all 3 of these supporting documents. Now, these documents should be kept on file together along with the corresponding lab report, as the data may need to be reviewed at a later time and analyzed for consistency or used for comparing historic data sets. In some instances, the data may be challenged in legal court where this supporting data or documentation must be defensible. Be mindful of transcribing notes. Often pump identification, calibration data, and sample name can get mixed up, especially when collecting multiple samples simultaneously. Time-stamped digital documentation is more reliable than handwritten field notes from 5 years ago. When applicable, downloaded data are transcribed the handwritten field notes and keep electronic files indefinitely unless program requirements dictate otherwise. So in other words, make sure that you have accessible, reliable documentation that if you had to go back 5 years to defend, you're able to pull up, you're able to read it, and you're able to respond to any deposition questions that might be asked. Lastly, let's talk about some advancements in calibration technology. Now, over the years, many advancements have been made in calibration technology instruments. Although soap bubbles and volumetric burettes are still used today, some technological improvements allow users to increase convenience while maintaining accuracy, precision, and stability using these advanced circuitry and sensors that are placed in today's instrumentation. Newer primary dry cell calibrators have been introduced into the market that can be configured to meet the user's calibration needs. These calibrators are more convenient to use compared to the soap bubble calibrators of yesterday, primarily due to eliminating the need to manually generate the soap bubble from the soap solution. As you can imagine, if you've used some of the older devices, having to generate soap bubbles for each sample is both time-consuming and, again, can be disrupted if the soap bubbles pop or if you have multiple soap bubbles that are generated with a single depression. Additional advancements allow the user to take full advantage of the ability to select between continuous or averaging modes. In averaging mode, the user may select a specific sample set to be averaged. Within other customizable settings, the user can define engineering units of measurement, date, time, temperature, and choose from a selection of languages in the device library. So with the technology advancements, you can really customize both what your user settings are and what your user output should look like. Additionally, internal sensors for standardizing flow rates based on reference temperature and pressures can be put in place. As I mentioned earlier in the presentation, newer calibrators will actually be able to show ambient temperature and ambient pressure. And because these are important factors, you want to make sure that your starting or pre-calibration conditions can be compared to your post-calibration conditions. The STP-corrected flow rates allow you to compare data sets in varying environmental conditions without the need for exterior calculations. So in the past, industrial hygienists have had to do this manually to make sure that you held a steady rate between your pre and post calibration sampling events. However, now with calibrators that can actually do this conversion or standardizing, you can actually have the instrument do it itself without having to do this calculation manually. So onboard computing can also data log the calibration events and perform statistical analysis on the deviations between readings. What do I mean by this? So in the illustration shown below, you see a red box around a 2 sigma, all right, which is your standard deviation. This really shows that each one of my individual samples within that 7-count sample set has a deviation or precision about it. You really want that tight shot group. So if you are showing a high 2 sigma, that means that your sample set is all over the place, that there's pulsation going on. This usually shows that there's some sort of yawing or bias of your pump itself. Your pump could have a poor stability in and of itself, or there could be bias introduced by those other factors, being the sample train or the calibrator. But it's important that if you want to record a stable flow set, that you have a really tight standard deviation. Some additional advancements include user interface. So now you have the capability with some newer technologies to actually have full touchscreen keyboards to input those user-defined fields that you want to have in your calibration log. Additionally, newer instruments are able to display the date of last calibration, the serial numbers for your calibration device, and the next calibration due date, which are all key elements of what you'd want to see in a calibration report. Now, tracking the usage of the calibrator through the displayed cycle count can be used for both the base and flow in this case, base and flow cell. Why is this important? So I can actually see how many cycles have been used since my last calibration. The reason this may be important is if I go send my unit in for recalibration and I want to go back and I want to see how far back I may be deviated from a desired calibration point, this really shows me how much usage I got over that period. Again, the newest piston-style calibrators have pulse-free valve technology, providing low back pressure to devices being calibrated. This is a unique and patented design feature which equalizes the pressure on the pump regardless of the puck travel direction. This feature also allows for minimal disturbance of the airflow generated by the instrument under calibration, providing the highest level of calibration accuracy. So having a stable piston moving up and down that doesn't slam up and down doesn't create that bias artifact. Therefore, a constant flow pump will not see a change in pressure and then react, creating that yawing effect. Some additional advancements include fixed sensing arrays. So as I mentioned earlier, older technology would have a top and bottom optical sensor. However, by having a fixed sensing array, there's no chance of those sensors becoming misaligned, and you can actually collect more data points along a fixed sensor array than you can with just a top and bottom optical sensor. And as you can imagine, having more flow rate data points ensures both accurate, reliable calibration throughout that calibration process. Calibrators can now also generate printable and digital calibration reports. These calibration reports display sample information, saved instrument settings, and individual sample results. This allows that calibration data to be added directly into your sampling reports and historical records to be retrieved and reviewed for statistical analysis. So this has really become user-friendly and a key feature in some of the newer technology out there. That concludes my presentation, but I did want to note that there were many resources that were referenced throughout the creation of this presentation. Here are the resources that were referenced. This will be available by RAECO in a published version of this presentation.
All right. Well, that's all the questions that have come up. If you want to know more about the technologies we supply, follow us on social media. We put lots of good technical tips on the blog at blog.RaecoRents.com. You can also follow us on LinkedIn and Twitter. We do record all these training sessions. You'll find them on YouTube or on our website, RaecoRents.com, and go into the training center. If there are some topics you'd like us to cover in our webinars, please send me an email with the subject. We have access to lots of product and process specialists. Please let me know what we should cover by emailing me at matt@RaecoRents.com. At this point, if we have no further questions, our presentation will conclude, and thank you all for attending. All right, thanks again, Aaron. Appreciate it.
All right, Matt. Take care.
All right, bye.